It's so tempting to try and sit there. So, see several announcements. I updated the reading list, just in case you were busy enough and had all the spare time. So the game plan for the immediate future is to talk about some machine learning models. The primary reason is so that when we go to Spark, we have something to do. And let's see, how many people here have already taken a machine learning class? So half of you can go to sleep for next lecture or two, and the rest of you will be frantic trying to figure out what I'm saying. And that brings up several things. One is how many people have successfully gotten their $100 account from Amazon? Just 1, 2, 3. $75. Unless you do something silly like spin up a cluster and let it run for a week, you probably won't go over $10 or $20. Even that, I mean, it's not like you're going to spin up a cluster of 50 machines, right? And you'll spin up a cluster of 2 or 3 and then run it. And well, this is on AWS, so you need an Amazon account. And I believe you want to create the account first and then apply for because I think they want your account number. So you should do that because I believe it takes some time to get, right? It took, how long? 2 or 3 days? So you probably want to get that started. That way when you come to me in a panic and I'll say, I told you. The other thing is, typically when you write Spark programs, you want to run them first on your local machine, just to get them running correctly. In the past, students with Windows machines have had some difficulty with that. I don't know the current situation. I don't have a Windows box to try it on. But I know they had trouble with all these versions of Windows, right? I mean, there's a Home Edition and Student Edition and Business Edition and Professional Edition and Super Duper. I mean, all these levels. I think the lowest level didn't work for them because it didn't have certain functionality. I don't know if that's the case or not. You can get an upgrade on the Windows version for free because San Diego State has a subscription to, well, it used to be called Microsoft Imagine. It's now changed its name to Azure DevTools. Although, and here's another warning, our subscription ends the end of next month. And in the past, they've given us free subscription that apparently is going away. And campus is planning on buying a year subscription. But the good news for me is I don't think I'll be involved, which means the process for individual students might be more complicated. And we haven't worked that out yet. But so if you want something from that store, you've got 30 days. I believe the key is good at least for a year or as long as you keep that one. I mean, It used to be called Microsoft Imagine. It's now called Azure DevTools. Azure. It's Microsoft Azure, their big cloud system. You'll be able to find, I mean, it's what they're making a lot of their money on now. They're sort of downplaying Windows and Office or any questions? We've got 3 more faculty candidates coming on campus, and then I will finally can breathe. Hopefully I get some more grading done this weekend, but we'll see. So I want to start talking about some machine learning models. And the first one I want to talk about is regression. When we talk about machine learning, there's all these terms that come up. There's supervised and unsupervised and reinforced learning and deep learning. So the 2 big categories are supervised and unsupervised. The first thing you know is they like to use these nice fancy terms. What does supervised mean? Oh, what it means is you say, here are 1,000 pictures of cats, 1,000 pictures of dogs, and now here's another picture. What is it? Right? The supervised part means you're going to tell it, here's your data, here's what it means. You just feed it over and over again, right? Unsupervised means, well, here's a bunch of data, tell me what you can, right? We don't tag the data as this is a cat, this is a dog, this is a cat. It's like, here's a bunch of stuff. You tell me what it is. And there's all kinds of types of things we can do. Classification is, like, okay, is this a cat or is it a dog, right? What is this picture, right? Here's a review. Is it a positive review or a negative review? Regression, we'll talk about, trying to predict what it should be. Clustering is another big area where, look, I have this data and I'm trying to figure out, are there clusters in this data separated out? So, this group represents something, this group represents something. Yeah, I'll talk about this a little bit later. And there's all kinds of algorithms, right, to do supervised learning. Let's see. And just a whole long list, right? Unsupervised learning, we'll look at some clustering out, k-means algorithms. Deep learning is this hot topic now, right? And the thing to know about machine learning is basically pattern matching. That's all it is pattern matching of different types. And so neural networks, what do you do? Well, it's like I said, you get a bunch of pictures of cats, and you tell, say, here's a cat, here's a cat, here's a cat, here's a cat, here's a cat. And then once you've trained it to know what a cat is, now we take another picture and say, ask it, is this a cat or not, right? and it's just matching a pattern. There's, self-driving cars are, sort of supposedly on the way. Tesla says next year or then this year. So there's this hacker in the Bay Area. What he did is he bought a car, and then he bought, sort of standard video cams, and he sort of taped them onto the windshield inside, and he connected it to his computer. He connected his computer to the car computer, and then he just drove around, right? He drove around, and he had, neural network just watch what he's doing and what the camera was, and after a while he could drive down the freeway and take his hand off the wheel, and it worked. But it was just, there's no network watching, right, what he did and what the images were. And once they trained it, once they got enough data, they could recognize, oh, there's a lane and there's cars, and you don't want to run into the cars, and you want to cross a lane, and that was it. He then tried to sell the system, and the federal government said, no, I don't think so. All right. What number goes there? So one was 19 and one was 14. $96. What? What we're doing is it's a pattern, right? And we're trying to figure out what the pattern is, right? Clearly, the plus doesn't mean addition because it should be 7, right? So one pattern is, you take 4 plus 1 and multiply by 1, and then you take 2 plus 5 and then multiply it by 6, you multiply by 2, and then, it's 3 plus 6, which is 9, and multiply by 3, you get 21, and then it should be 96, right? Or it could be, I just get 5, and then I take the 5 and add it to this result, and I get 12, and I take the 12 and add to this one, I get 21, and then I take the 21 and add this, and I get 40. So we have 2 patterns, right, that match up to here. Which one's right? Right? Given those 3, the first 3, they both match, right? Right, so this is no free lunch. Which basically says that, if you've got a machine learning algorithm that's good at detecting a pattern, there's another pattern it's not good at detecting. So there's been examples of people trying to trick face detection, in part because it's an interesting, exercise to try. And some people don't like the idea that when you walk down the street now, cameras can detect and track you, right? And so there's all example of adding, weird things to your face, which will create a pattern that face detection algorithm was not good at detecting. I've also seen examples of where they take a picture, right, and then they recognize that, and they put in random pixels of different color, individual pixels, so the human really can't see it, right? You look at it, you don't know if they're different, so you and I look at it and say, well, there's no difference. And the machine learning algorithm can identify the cat in one, and it can't identify the cat in the other, even though it's the same picture, just slightly modified. So it's just important to understand that there are limits to these things we're going to be talking about, right? And for the common people, it's like, well, there's this crazy thing called machine learning or AI, and it's going to take over the world. But it's just pattern matching. Okay, Rodney Brooks was a very famous roboticist. He still is. He was at the MIT Artificial Intelligence Lab, and he was a guy who said, if we're going to do robotics and learn to make them smart, you need to start like evolution, and we start with insects, right? So you start little robots and make them work. So he has this paper. First one, Zamara's law. We tend to overestimate effective technology in the short run. We're going to have self-driving cars by the end of the year, right? But we underestimate the effect it's going to have long term. The most famous example of this is GPS. The GPS system was created for the United States military. That's why it exists. The reason they created it was so they could pinpoint targets. So you could have, really smart bombs that land exactly where you want them to go. Entire goal of the GPS system, period, right? It started in 1978. Launch all these satellites. So we can, like I said, we want the bomb to land on this square. It's going to land on this square. It wasn't until 1991 they actually, the first time they actually used it for that purpose. And they weren't quite so sure about it for a while, right? But you all use GPS all the time, right? All your cell phones use a GPS system to tell you where you are, to help you drive places. And when you go on Google Maps to see how the traffic is, how's that done? Our roads don't have sensors on all the freeways. Some of the freeways do, but the local streets don't, right? They don't have sensors marking the traffic and seeing how fast it's going. All that's done by your cell phones telling Google how fast you're going. And they collect it and then they distribute it. It's on mobile phones. These days, UPS, if you sign up for the right service, when you expecting a package, they'll show you where the truck is, right? Bus systems will show you where the buses are, so you don't have to worry about where they are. It's used the electrical grid because we need to synchronize all the power, and we need to worry about where you're coming from. And it's important that all these power plants, when they put power on, the phase of electricity has to be the same. And the farmers use it to figure out when they should plant, where they should plant, what they should plant. So in the short term, right, it was going to be used by the military, and it took a long time for that to happen. And no one saw that basically billions of people are going to use it on a daily basis. Right? Nobody saw that coming. And we train these things to recognize certain activities, right? This is a cat, right? We train it to play Go, we train it to play chess, but that's all they can do, right? They can't go beyond that. Exponential growth is not sustainable, right? If you took a biology class, presumably told you all, bacteria will self-divide. There's 1, there's 2, then there's 4, then there's 8. But if you keep on doing that indefinitely, pretty soon the planet is covered, right? Mile deep on bacteria, no one can else live, right? How's that going to work? And we get seduced by that because for so long we had exponential growth in the power of our machines, right? Moore's law, it's dead, right? We're no longer. It used to be you replace your machine every 3 years. Why? Because after 3 years, the new machines are so much faster and so much more powerful than they were before. It's like you can't do that anymore, right? And so we no longer have this built-in exponential growth of our processors. And why is that important? Why do neural networks and deep learning work? They were discovered decades ago, right? But they didn't work. And all of a sudden, 5 years ago, they started working again, or started working and being useful. And it was like the old timers and AI were like, what happened? I mean, what new discovery was there that made this idea we had discarded decades ago because it just wasn't practical? And the answer was faster machines. That's it. And yeah, this deep learning, right? The breakthrough paper was in '86. And they literally abandoned the approach. It's like, it doesn't work. I mean, we can't do anything with it. And now it's a hot thing. And the side is that, people, AI is hot, and but there's always this AI goes through these cycles, and the question is, where's the next big idea in AI coming from? Well, right, because the current big idea is, well, it's like 30 years old, right? Now the basic idea is we're going to create a model, right? So all the machine learning algorithms, they produce a model, and the model we can use to make predictions or explain what's going on. And here's just examples of very simplistic models, right? For example, Amazon knows that you decrease latency by a millisecond, how much more that's going to increase their daily revenue. They know this. This is a formula they know, and right. We can also model. You just electorate by we sampled them, and we know that certain types of people will favor Trump by a certain percentage. Right? It's a model. But models are just approximate, right? That's not the real thing. For a long time, for centuries, Europeans, the theory, the model was the world was flat, and it worked, right? That was, if the fastest you can do is get on a horse and ride it someplace, mapping and modeling the world as being a flat surface works. It did cause logical problems, because then, is there an edge, right? Is there an edge? What happens when you go over it, right? And then it's like, well, what's holding the whole thing up, right? And so at one time there was this theory that Earth is sitting on a big turtle, and then what's the turtle on? Well, it's standing on 4 other little turtles, right? And then what happens next? Well, there's turtles all the way down. But then, some smart people started saying, look, when you watch a ship, right, the bottom part disappears first, but you can sort of explain that away by optics in the haze, right? But eventually it's like, well, we sailed that way and we came back this way. Doesn't work on a flat, so it's a sphere, right? So now we can model it as a sphere, and that, right? And that worked as a model for a while, but the problem is it's not precise enough, all right? If you actually want to launch a satellite and put it in geosynchronous orbit, or you want to, launch a missile from, say, North Dakota and have it land in Moscow, the navigation you need to do is not good enough to say the world is sphere. You have to know more precisely. So these are all separate models, but each one approximate reality a little better, but that doesn't mean they weren't useful, right? For most people's purposes, we could consider the world flat and it works, as long as you don't think about the ramifications, what that means in terms of what happens, what's the sun thing doing? How does that work, right? And so we have to ask is, does the model we're using provide useful insights or predictions, right? And how accurate are those predictions? Right? And science is full of examples of where we had these models of how things work, and later on we discover they're wrong, right? Yeah, and when is that useful? And yeah, how accurate is it, right? And it's usually not just one thing, right? So in this Amazon case, right, its daily revenue depends on a number of things. Yes, the latency is important, because if it takes too long, people will get bored or they go elsewhere, right? But it also depends on the price of the items. The prices are more expensive, eventually they go elsewhere. The one-click thing in Amazon, right? Just to reduce friction, that increases revenue. Amazon, all these big web companies are daily doing multiple experiments every day, right? They're tweaking the layout of the page a little bit, and they're doing A/B testing. And some people get this version, and they track that and see how long you're on the page, whether you actually buy the thing, to figure out if they can just improve their page layout, changing the color, changing the size of the font. I mean, we're continually experimenting to figure out how to make us better buyers or more frequent buyers. And so if we're going to build a model, right, we may want to include some or all these factors. And then what happens then is it's going to, each one of these factors basically becomes a dimension in the model, right? And the more dimensions you're in a model, the bigger the space is modeling, right? And that causes problems because, well, if I've got a two-dimensional space, it's fairly easy to search, right? A three-dimensional space, now it's bigger, right? And so I need to find things in that space. It's going to take longer, and I'll need more data to create my model. If I got a four-dimensional model, it just increases the size of the space, which makes things more complicated. And we need more data to deal with it. So one of the techniques we will talk about is reducing dimensions, right? Can we take these 1, 2, 3, 4, 5, 6, like 9 dimensions, and can we squash it down to 3 dimensions that produce the most solid effect? Yeah, and these are all independent variables, right? And then the revenue becomes a dependent variable, right? Yeah, some features are more important than others, and things are stochastic in nature. They're not. If you really need something tomorrow, right, and you're too busy to go to the store to get it, adding a few milliseconds to the lower in the web page probably doesn't matter to you. Like, I need it now, right? And that's only when I get it. So I don't care what the page looks like. I need that thing. I need it tomorrow. And you're the only. I mean, I don't have time to go out and get it, so you're stuck, right? So the first model, right? Very simple regression. Yeah, that's wrong. I forgot to delete that bottom part. But it's just, there it is, right? It's just relation between the dependent variable on its independent variables, right? That's it. Yeah, so there's different types of regression. The simplest one is linear regression. And so, yeah, we want to know, how do we generate the model, what's the error in the model, and the effect of the independent variables, right? So it's called linear regression because we're going to create a linear function for it, right? Now, the first time I saw this when I was undergraduate, mathematics, it confused me. For a long time, when they wrote functions, they were like f of x equals this, right? And you say, oh yeah, f is a function. I put x in, and but mathematicians also will do this. They'll say y equals 2x plus 3, meaning that's okay. Y is the dependent variable and it depends upon x in that way. Instead of writing f of x, they'll say y. And when you do linear regression, all the models, all the tools that we use do it this way. They say y equals, right? And so, yeah, y is the dependent variable, x is the independent variable, and that's our model. I mean, it's just fancy terms for we have an equation, right? But the problem is when you gather data, you don't get a straight line in the real world, right? Because there's noise, depending on what you're doing, right? If you're looking at the latency, the problem is different people experience different latency, even if they're on the same site, depending on where they are. Different people have different sensitivity to latency, right? So when we're measuring latency, it's not like everyone reacts the same way and everyone computer acts the same way and the network works the same way, right? So it's the information is going to be noisy. And so then you start getting things like this, right? And when you look at that, it looks like it's a linear line with some noise in it, right? Which is good because that's how I created the graph, right? I just took a straight line and I just added random numbers to y and plotted it. And so we can assume that this is the case, right? It's a linear equation. And then we want to compute the line that best fits the data. And this, a common way is to use a least squares fit, right? There are other ways of regressing on a linear system. And then we get the line, right? And we saw the seaborne plots will do that for us, right? You do a scatter plot, and then it'll plot the regression line, and actually the confidence interval for where the regression line should probably is. And the other conceptual leap when we're talking about these models is a stochastic, right? So we're used to saying, oh, I put 5 in for x, and then I'm going to get b times 5 plus a equals y, right? But in just a stochastic, what this equation really is talking about, oh, x is a stochastic variable, right? So we're going to take on these values at a certain distribution, and then y is again a distribution based upon this formula. And when we get to create the models in scikit-learn, then x becomes actually a vector, right? And y becomes a vector of values. And yeah, the goal is to minimize this residual. This one is like, yep, I think that's linear. This one, well, it's still line-like, but there's more noise, right? We could still plot it. This one, I don't think that's linear. We can still, right? This one, it's still weird. I mean, it's weird, right? Because yeah, there's a line there, but what does that mean, right? That doesn't mean I cannot plot a line, right? I can't plug in the equation to compute the least squares and just draw this line. The same thing here, right? But would that line be a good representation of the underlying process that's generating this data? Probably not, right? That doesn't mean we can't draw a line. This is, there is this online comic strip, XKCD. The reason it's called XKCD is that the author said he was looking for a URL that was small and wouldn't clash with anything, and XKCD was not taken, so he took it. And he likes to do comics on science and math, and I guess it's called Science, Math, and Romance, right? Um, and yeah, and it's like you can draw the line, but it made more sense to draw a constellation in that data. Right? And the problem becomes, yeah, how do we tell when they're related? When is a linear regression a good model? So yeah, we have, of course, mathematicians and statisticians have been on this for a long time, right? And so they have several measures. One is the covariance. And what does this mean? Well, the bar means the mean, right? So we're looking at all our data and how it differs from where the mean where it should be. We do the same thing for y, and then we multiply dy by d times dx, and we sum over all the values and divide by n, and that defines this thing called the covariance. And it turns out that if x and y are really related, then their mean should vary in a similar way, and so if there's no relationship between them, then the sum should basically be 0. And if the values are positive, then it indicates they are related. So, and the more positive it is, the more likely they are related. And if it goes negative, then they're inversely related. So let's look at a simple example. So I'm gathering data, and someone bought something for £3 and it cost them 9, and someone else bought £7, it cost them 24, then £10 cost them 38, and then we want to model that, right? Are these things related? But we can convert pounds to grams, right? And a good portion of the people in this room are probably more used to. Well, India use kilograms, right? You got rid of the British pounds, right? Now, one thing to note is, if I measure in grams or pounds, it's the same the same relationship, right, between the price and the weight. And so using pandas, we can compute the covariance. So I create a series of the costs and the pounds, and also the grams, and then I can just call COV on the cost, and because of the pounds, I get a value of 50.8. If I do it for grams, I get 2,000, actually 23,000, right? And then if you really want a large number, convert, right, the price into Indian currency, and it becomes 1,000,000. But it's the same relationship, right? And it turns out that the relationship is symmetric. So if I compute cost on pounds or pounds on cost, I get the same value, which is you expect because you're just taking one and the other and multiplying them together, and right. We can also use data frames to compute the covariance. And so here I just took, create a data frame, one cost, pounds and grams, right? So I basically reproduce this table in a data frame, and then I can just call covariance on the data frame. Now it doesn't know which ones we want to compare, right? So it does them all. Right, so here's cost in pounds, those are 50. And then there's cost in pounds is 50. So it's symmetric, right? Because it's, and then of course you expect cost and cost to be related positively because they're the same thing. So they should be basically identical. But again, the scale changes the value, right? Well, the thing to keep in mind is that we're looking at these things, they have units, right? Remember your physics classes where you had to do all these problems, they forced you to an equation to put on the units, and then you had to, like these cancel, and then you'll tell you, oh, this is something meters per second, right? Well, that's what you got to do here, right? Is we need to, we really are talking about pounds per, right? Or we're talking about, grams times, right? That's why the numbers are different, because there are units involved. This is a common problem with data, right? There's units involved, and so how do we deal with it? Otherwise, people in India think that this thing's really related, and we think, well, it's pretty related, right? So the standard technique is to normalize data, right? There are a number of different ways of normalizing data. One way is just divide by the maximum value, right? So here are our values. So I'll divide the cost by 38. And so that becomes 1, this becomes less than 1, right? Divide this by 10, this becomes 1. And then I get this table, right? And if I wanted to compute the amount in grams or the amount in pounds, I get the same result. In Python now with pandas, I can just take my pounds data and divide by its max, right? And I can take the cost and divide by its max value, and it will divide each element. And then I can just compute the covariance. And I get, So important lesson is you have to be careful about the scale of your data. Sometimes it doesn't matter, but sometimes it will. And so we can normalize it to get rid of that scale effect. Of course, like I said, the mathematicians and statisticians have been doing this for a long time. And so there's always going to be more things they can apply. Pearson's correlation is basically covariance divided by the standard deviation of x times the standard deviation of y, and this will normalize it. There's no units, and it goes from minus 1 to 1. And minus 1 means they're basically identical. 0 means, as far as we're concerned, they're not related. And minus 1 means that they're inversely related. And of course, all the standard toolkits will compute this, right? So in Python, it's core with 2 R's. It turns out that in Julie, it's core with 1 R. And so calling core on either one gives us 0.998, which indicates that they're highly related, right? So far, so good. Of course, then we get this nice little chart. This is famous. Someone actually published it. I could get a published paper out of it. So various plots, right? And then the Pearson's correlation value R for all of them, right? So yeah, 1, that sure looks linear. Minus 1 because it's going the other way. And then as we go through, we're getting more and more disorder. And so 0, like, yep, perfect, right? And then we go, the second row, oh yeah, it's 1, 1. And the problem is, what this, this can't compute that because it becomes undefined because of, right? And then these are all minus 1s. The bottom row is the real fun one. Why? That's 0. There's definitely a structure there, right? What is a structure? I don't know. But that's 0 when you compute it. They're all 0, right? Saying that somehow they're not related. I mean, look, come on, there's definitely a structure. There's something going on here, right? That's a circle. We all know it's a circle, right? And we all once knew the formula for the circle, right? So we know there's an equation there we can use to compute the circle, and it's just all they did is they did the circle and they added some noise to it, right? So there is a relation there, but all these calculations are statistical, right? Just because statistics say, oh, they should be related, doesn't mean they necessarily are, right? And of course, if you want to be expert at this, you take, you get a degree in statistics, each level you go on to how do I then distinguish between these things, and go on and on and on. So regression, right? How do I compute this line? So we can draw this regression line, and we saw that when you produce a scatter plot in Seaborn, you can have it draw the regression line and then the confidence interval. But of course, it makes for a nice plot, but we can't use that line to do many predictions because we don't know what the slope of the line is, right? And that's only because it was the 2-dimensional data. What happens is 3-dimensional or 4-dimensional, then a common way is to use the least squares fit. So you basically and trying to minimize the top equation, right? Where you basically compute the distance from that line to all the points, and then you take the square of it, and you want to make sure that is minimized. But of course, we don't have to do that. We're computer people, right? So the first thing we do is write a program to compute it for us, and then we can just call a function, right? So here's an example. So standard imports, generate a number generator. I'm going to generate 50 random numbers, and then I'm going to multiply them by 10. So these numbers are between 0 and 1, so now I get between 0 and 10. And then I'm going to, here is my true line, my true relationship, but I'm going to add some noise to make it look like the fake data, right? Rather than trying to go find some process and measure it and get the data. So this is my fake data, and then when I plot it, yeah, it looks sort of random. I mean, it's linear, but there's some noise, and so we can pretend it's real data. And we can then, compute the correlation as 0.99. So statistically, it says that they should be related, and our eyes tell us that. And given the way I generated it, yep, they're related. And so this is just our fake observed values. So now we want to create that regression line. But this is linear regression is machine learning algorithm. So we need to use machine learning. And in the Python world, the standard is scikit-learn. And so we're going to import from scikit-learn the linear regression function. And then what I do is x was just a vector, right? Scikit-learn for independent variables, it requires a two-dimensional matrix because for one, it's like, why are you bothering us computing a model on one independent variable? I mean, really? I mean, is your problem so simple? Why don't you just go use a calculator or something? So they expected to have multiple, right, independent variables. And then that's called in regression. And there are various parameters, and we wanted to, look at the intercept, right, where the line hits the x-axis. And then you just give it the x values and the corresponding y values of your data, and then say fit the model. We've now trained a model. How about that, right? And pretty much all the machine learning algorithms are like this, right? You pick the algorithm, and then here's your data, except you really want to divide your data set into three pieces. One is the training, right? And then validation, and the third one is testing, right? And last night I read an interesting article saying, you know what? Most researchers, they use the testing data and the validation data. What? Like, no. All the classes say three separate, right? You take your data set, divide it into three pieces, and you don't mix them up. And they say, no, all the researchers, it does make your results look better. Once we got the model, we can ask for its coefficients. Right, it's a linear model, so it's going to be y equals a times x plus b, right? Since I only have got one independent variable, and so that says that's a times x, right? And the intercept is, And remember, our equation was 2x minus 1, right? So that's pretty close, right? And so we now, this becomes our regression line, right? And so literally what I can do is I can, create a function which I pass in the model, and it grabs out the coefficient and intercept and returns a lambda, which basically is that function. And then I can then, well, I forgot to include that chart, but what this is doing is the linear space, it creates 50 points starting at -1, evenly spaced up to 11. And that becomes where I want to evaluate the function. And I can then call my function on those points. And the nice thing about Python, it does the right thing. When I pass in a vector into a function with respect to a value, it actually does it, elements at a time, and then, right? Isn't that nice? We don't have to do the for loop. And again, most of these libraries do that, right? If you pass in a vector to a function expects one value, it just evaluates that function all the points for us. And then I plot, well, there's the x values, and here's the y values. Oh, and this is scatter plot is doing another plot. And there it is, right? There's the regression line. It looks pretty good. And of course, I just had to do it. It was like, oh, I have to do this, right? Well, so yeah, we can compute the regression model ourselves, but it's like, they actually will do it for us. Right, so here again, I'm creating those 50 evenly spaced points, and I have to convert it into a two-dimensional thing, and then I can call predict on the model, and it knows the coefficient, and it knows it, right, and it will then basically do what I just did in the previous slide. And then, yeah, it sort of looks like the same, right? And we did it before, right? With Seaborn. And so what I did is I did both plots, right? The X fit and the Y fit from the previous slide on top of the Seaborn plot. And you probably can't see it, but the confidence interval stops at 0 because that's where the data stopped. So the Seaborn didn't do any further, and it stops at 10, but I went up to 11. And so the regression lines are identical, right? It's nice to know, right? So scikit-learn has, well, here's a list of all the generalized linear models we can use. Ordinary least squares is just one of them. And so again, the problem we're faced with is for us, it's, they're all programmed for us, right? So I could literally pick any one of these things, and it's literally the same, almost the same line of code, right? I mean, literally, what did I do here? I mean, That's it. All I have to do is, instead of importing linear regression, I can import one of the other ones and do the same set of operations, and we get the same, I can carry out the same computation, but the question becomes, when do we use which one, right? And that's one of my, I won't call it a nightmare, but it bothers me in the sense of, these days, for example, Apple has a tool where if you want to train a neural network, you can drag and drop your file, which contains the data, onto Xcode, and it will then pick an algorithm for you. It will then use that data to train itself on and spit out the model. Like, you maybe that's a little bit too easy. When the Mac first came out, I mean, long before people were born, right? There's prehistory here. It came. One of the innovations was that there's laser printers, right? And you could connect the laser printer to the computer, and you could then make write or to create the document. And it's like you no longer needed these fancy people who who knew about how to lay out text, right? And what was the result? People created the most ugly, hard to read things like, oh, I can use 5 fonts. No, you don't want to use 5 fonts because it makes it hard to read. Oh, I can, right? The World Wide Web comes out, I can create web pages, right? Oh, God. I was like, people have these flashy things and these big counters. And it's like, oh, don't do that, right? The problem is if you don't, you have to understand the tool and what it does for you, right? And you have to understand the effect. And that's what I think we're facing now, is because now all these algorithms are available to us, and you just, like I said, just those 3 lines, you're done, right? And you just pick the one algorithm and you flip a coin, right? And I'm going to use this one, but it may not be the right one. And that's why you really want to take a course on machine learning, right? So you go into much detail on when to use them. And if you really want to be a true data scientist, you go take that course and statistics courses to really understand all the mathematics behind all this stuff. Yeah, we can overfit the data. If you ever took geometry, you remember if we had 2 points, determine a line, and then 3 points, determine a quadratic, and 4 points, right? So if you give me n points, I can find a polynomial that will go through all those points, right? And so, for example, here's my data points, right? If our goal is to find a function which minimizes the error, right, on these data points, I find a polynomial that will go through and hit them all, right? But the problem is, do you really think this line is a good model for this process? Probably not, right? Because this is like, that's just too weird. We're forcing this polynomial in. So we're overfitting the data to make the errors get smaller. But as a result, we're creating a model which is going to have some huge errors in other areas, right? It's not going to be a very good predictive model, particularly since it's probably headed like way down here, right? And so it's going to say this, eventually it goes negative when it's like, no, I'm sorry, it doesn't go negative, it keeps on going positive. So there are a couple of ways we can ask, is linear regression a correct model? One is look at what's called residuals, and then there's this value called R squared. The problem with doing these add-on things, you forget somehow to hide it up. So residual, you basically take the difference between the observed value and the predicted value, right? So here I'm creating, right, my observed values, my fake data, and then I'm going to, get the model, fit to it. And now I'm taking, right, here is my predicted values, here's my actual values. I subtract them off. And what should happen is that plot should look random, right? And it should be centered around 0. Why? Because if it's linear, then you'd expect values half the time be above and half the time below. And since I'm subtracting off the actual values, then that's basically turning the line to 0. So if there's a pattern here, then your system, your data is probably not linear. Right? The video should be randomly distributed, and the sum should be close to 0, and the mean should be close to 0. Now, I think we'll stop here, and then we spend a minute enjoying whatever it is we're hearing.